So we're going to be presenting on RSA. First, you have to understand the concept of asymmetric encryption. Normally in symmetric encryption, you have a key that can encrypt a message to make it unreadable, and then take that encrypted message and decrypt it. But in asymmetric encryption, there are two keys, the public key and the private key. The public key only encrypts messages, and the private key only decrypts them. So you can make the public key public, and people can encrypt messages and send them to you, and then only you can decrypt it with your private key. An important concept to understand for RSA is modular arithmetic. Modular arithmetic is math that's done mod some number. Mod, which is short for modulus, just means the remainder. So if you do something modulo 10, for example, 13 and 3 and 93 are all equivalent. So the first step in RSA key generation, where you make the public and private key that correspond with each other, is to pick two prime numbers, p and q, and you usually have an exponent already picked out, e, which has to be coprime, meaning it doesn't share any factors with p-1 and q-1. You multiply these primes together to get n, which is going to be your modulus. N and e together make up the public key. P and Q are then used to generate the private key. The security of RSA comes from the fact that you can't find P and Q from N in a computationally efficient way. To encrypt a message M, which is just a number, using the public key, N and E, you raise M to the power of E is short for exponent, and you take that modulo N, and it gives you a message, an encrypted version of the message C, which is between 0 and n. The next step is generating the private key. This makes use of a totient function, one example of which is Euler's totient. Totient functions satisfy a specific rule that we'll talk about later. The totient of n can only be computed efficiently if you know p and q, in which case it's just p-1 times q-1. You then calculate an integer d, which is part of the private key. D is the modular inverse of e, mod the totient of n, which means that e times d is equivalent to 1, modulo the totient of n. So now d and n make up the private key. To decrypt a ciphertext C using the private key, you raise C to the power of d, and then you do mod n. And that will give you back your original message, m, which was used to generate the ciphertext. So looking at the equations for encryption and decryption again, if you substitute the equation m to the power of e for c in the decryption, you can see that the central property that makes RSA work is that m to the power of ed is equivalent to m mod n. But why is that true? Well, the secret behind this comes from the property of totient functions, which is that for any integer a coprime to n, a to the power of the totient of n is equivalent to 1 mod n. If you'll remember from the definition of d, e times d is equivalent to 1 mod the totient of n. So we can rewrite that by saying that ed is equal to the totient of n times some constant k plus 1. So now plugging that in for ed, and then just using basic rules, we can find that m to the ed is equal to m to the power of the totient of n to the power of k times m. Now using that property of totient functions, we know that m to the power of the totient of n is equivalent to 1 mod n. So we can just substitute 1 into the formula from the last slide, and we get that m to the power of ed is equivalent to m mod n. And that's basically how RSA works. Does anyone have any questions? Well, too bad, because we're gone, and this is a recording. Suck it.